My name is Noah Anima, and I am the project manager for Across the Street Engineering. As a recap from last presentation, these are our responsibilities for this semester. As a transportation engineer, I am responsible for transportation improvements along the Silhavy sector of the project. Jolie, our other transportation engineer, is responsible for the Chapel Drive extension. Bella is our structural engineer, and she is responsible for the design of a new academic building, shown by the orange rectangle on this slide. Allison is our water resources engineer, and she will not be here this morning due to sickness, but we will be hearing from her shortly via video. During this presentation, we'll each take a turn to present the alternatives that we have looked at this semester, and we'll also present which ones we have selected. I'll kick things off by looking at transportation at Silhavy Road. As a recap from last presentation, I will be realigning Silhavy Road to improve substandard curves that currently exist. Along this alignment, I've been asked to provide facilities for pedestrian and bike travel. The city has also asked our team to redesign the intersection of Strongbow Center Drive and Silhavy Road. Finally, new and improved parking is needed for the VU baseball facilities. I'll start off by looking at three different alternatives that I have for intersections at Strongbow Center Drive and Silhavy Road. First alternative is a one-way stop shown on this screen. On the bottom right of this screen, you'll see the individual level of services and delays for each turning movement. The benefit of this alternative is it is the lowest cost both for construction and maintenance. It also has a very good level of service and low intersection delay. The disadvantage of this alternative is there are some safety concerns for pedestrians, especially crossing northbound and southbound road. The second alternative is a signalized intersection. This intersection will be safer for pedestrians, as a pedestrian phase can be included in the signal timing. It also has a good level of service. It's an A again. The disadvantage of the signal is it's an extra $550,000 approximately. And it does have a high delay for eastbound turning movements. And while it does have a low intersection delay, it is higher than the other two alternatives. The third alternative is a Seagull intersection. This intersection has the lowest intersection delay of all three alternatives. It is also safer for pedestrians than a one-way stop, since a pedestrian refuge can be constructed within the channelization barrier. The disadvantage of the barrier is that it will be a larger footprint and higher construction cost. There is also an issue with the potential for snowplows to run into it during the wintertime, which would be a higher maintenance cost. I've selected the one-way stop as the preferred alternative. The reason for this decision was the low construction and maintenance cost, as well as low intersection delay. Now I'll move on to talking about alignments. This is my first alignment alternative. Starts off at the top, following the existing alignment of Silhavy Road, and then winds around the wetland itself before continuing on. The curve around the wetland is an improvement from what we have currently in the existing conditions. This new design would have a 150-foot radius and 6% super elevation. And with those parameters, we can reach a design speed of 25 miles per hour. This alternative is the cheapest alternative because it uses the footprint of the existing roadway as much as possible. It also has a low wetland and floodplain impact by avoiding the wetland by going around the south of it. And finally, it has direct access to the hotels and businesses that are already along Silhavy. The disadvantage, it's not the most direct link between what will be Chapel Drive extension up the top and Strong Road, Silhazy intersection. And because we're going around the wetland and we have that tight curve, it's designed for 25 miles per hour instead of 30 miles per hour, which is what's desired by the city. Alignment alternative 2 is a more direct alignment, and it does cut through the floodplain. As you see in the middle figure on the slide, about half an acre of the floodplain will be impacted by the road cutting through the floodplain and the grading that is associated with that. Plus, a new culvert will be required at that location. Continuing to the southwest, we'll need a new intersection and a new roadway link, taking us down to the existing buildings and hotels. The benefit of this alignment is it is the most direct, and it can be designed for the 30 mile per hour design speed. But it does have several disadvantages. There's significant grading and excavation that will be required. This leads to higher construction costs. It cuts through the 100-year floodplain, so mitigation will be needed for that. There's a greater right-of-way impact. It also requires a new intersection and is less accessible for the hotels and businesses. I selected alternative 1. The reason for this decision was the low cost and the lowest right-of-way and environmental impact. In addition, no additional intersection would be required, and it is the most accessible for the hotels and businesses. I have designed the layout for 2 parking lots. This first one follows the footprint of the existing lot at Orville Drive. The second parking lot is on Silhazy Road. I strategically located this lot on a flatter area to minimize grading and excavation. And I also located it south of the overhead utilities, so I'm avoiding those utilities as well. I've estimated the construction cost for my preferred alternatives to be $1.8 million, with a 20% contingency that brings it up to $2.1 million. You can see some of the major components of the construction costs on this slide. I did use the INDOT standard pay item spreadsheet and the unit cost estimate method for calculating the construction cost. I looked at about 26 different items to calculate this cost, but those 4 are the top costs for this project. At this time, I'll turn things over to Jolie.
Hi everyone, my name is Jolie and I'm the other transportation engineer for the Eastgate Development Project, but I focus on the Chapel Drive extension portion of the project. So just a little refresher on my scope from last time. I was tasked to create a roadway link between Sturdy Road and Silhazy Road, and also redesign the intersections of Sturdy and Chapel Drive and Silhazy and Chapel Drive. And along with that, I designed a parking lot for the new academic building that our structural engineer Bella will be designing. So to start off, we'll take a look at my intersection alternatives for Sturdy Road. So the first intersection alternative that I looked at was a roundabout alternative. And the pros of this roundabout are that it has a level of service A and it has very low intersection delay, as well as low maintenance costs because you don't have to worry about a signal or anything. However, the cons are that there are a lot of safety concerns for pedestrians. Construction costs are really high for the roundabout. You'd need to have a lot of right-of-way, and it's difficult to construct because of the geometry of roundabouts. The next alternative that I looked at was a signalized alternative, and this has 35-foot turning radii on all corners of the intersection. The pros of this intersection are that there is a level of service B, a low intersection delay, it's much safer for pedestrians, and the construction costs are lower. However, some cons are that the maintenance costs are higher due to the signal, and you would still need to acquire some right-of-way, and while Across the Street acknowledges that the roundabout had a better level of service, the difference in cost as well as the fact that the level of service difference wasn't really that much, we've selected the signalized alternative for the Sturdy Road and Chapel Drive intersection. So looking at the Stillhaven Road and Chapel Drive intersections, the first alternative that we looked at was a two-way stop, with the two-way stop having stop-controlled movements on the eastbound and westbound approaches. The pros of this is that it has low construction and maintenance costs, as well as the fact that it's very easy to construct. However, the cons are that during the PM peak, there is a level of service C, and during the AM peak, there's a level of service D, which is not ideal, and there is a much lower traffic capacity. So the other alternative that we looked at was an all-way stop, and so that's shown here. The pros of that are very similar. There's low construction and maintenance costs, since all we need are some stop signs and pavement markings, and it's very easy to construct. It is an intersection level of service B, which is very improved from the other alternative. However, there is a higher total intersection delay than the two-way stop, because obviously everyone is stopping now and not just the two movements. But ATS has selected the all-way stop approach as the preferred alternative for the Stillhaven and Chapel Drive intersection. Looking at the alignment alternatives, the first alignment alternative proposed is shown on the screen, and it has 5 horizontal curves, including one that goes through the wetlands area while crossing Node Creek. And then the second alignment alternative has 3 horizontal curves, however, there isn't one going over Node Creek. So looking at the pros and cons of both alignments, there's limited wetland impacts for both of the alignments, and they are both pretty direct as far as getting from point A to point B. However, alignment alternative 1 is going to have higher construction costs due to the fact that there is a curve while crossing Node Creek, and then there are also more horizontal curves requiring us to have a larger footprint. And so for that reason, ATS has selected alignment alternative 2 as the preferred alternative for the Chapel Drive extension. Lastly, I was tasked with designing a parking lot for the academic building. And so this parking lot's design has not changed since our last presentation. It is still 142 spaces. However, there have been end cap pavement markings added to ensure that a WB50 truck would be able to have room to turn within the parking lot. So leading into the cost estimate, using the NDOT pay items list, I found that my total cost was about $3.6 million. And then when you add in the 20% contingency, it bumps up to about $4.4 million, with the most expensive parts of that construction cost estimate being the excavation, HMA, aggregate, and the traffic signal. So with that, I will pass things over to our structural engineer, Bella Palmer.
Hi, my name is Isabella, and I am the structural engineer that will be representing Across the Street Engineering in the Eastgate Development Project. So just to recap the structural project scope, I was tasked with designing an academic building on the Eastgate property that is about 30,000 square feet. That will include classrooms, offices, labs, a covered outdoor space, and a 240-person auditorium, as shown in the figure on the slide. So in order to satisfy the project scope, 3 alternatives have been evaluated. These alternatives are a single-story concrete alternative, a single-story steel alternative, and a 2-story steel alternative. As shown in the table on the slide, there were 5 key parameters that were used to evaluate each of these alternatives. As you can see from the list, safety is missing due to the fact that it is assumed that with whatever design is selected, that the building will be constructed with safety and will meet all design standards. So just to take a look at all of the criteria that have been used to evaluate the buildings, I will evaluate construction cost, maintenance cost, feasibility, environmental impact, and space efficiency, and all of these factors as well as their weights will be discussed later within the presentation. So to talk about the first alternative, which is the single-story concrete alternative, this alternative will be 28,600 foot squared, and the perimeter will be 772 feet. The design cost for this alternative will be a little bit over $7 million. and the floor plan is shown on the slide. This floor plan is the same floor plan from our previous presentation. The space allocated and everything has remained the same. For this alternative, we will use reinforced concrete beams with a strength of 4,000 psi because we will use normal weight concrete. These beams will also include rebar that will be built with A615 steel, and the strength of that rebar will be 60 KSI. Using the length to depth ratios that were mentioned in the technical memo as well as the previous presentation, the beam depths will be 14 inches and the girder depths will be 21 inches. For the single-story steel alternative, the area and the perimeter remain the same because the floor plan is identical for the single-story alternatives. However, as you can see, the construction cost is significantly lower, being at less than $7 million. For this alternative, we will be using W beams, and the steel that is used is A992 steel with a strength of 50 KSI. Similar to this last alternative, the beam depths will be the same using W14 beams for beams and then W21 girders. For the two-story steel alternative, the area of the total area of the building will be 31,000 square feet, which is slightly larger than the other alternatives. However, the perimeter will be less. Additionally, the cost will be significantly higher at almost $8 million. For this alternative, the same materials will be used as the single-story steel alternative. However, W16 beams will be used instead of W14. So just some additional considerations. So in all of the previous alternatives, the covered outdoor space was not considered. This is due to the fact that limitations with RS means does not allow for an accurate calculation alongside the rest of the building. So the covered outdoor space was considered separately, in which it was assumed that the cost of all of them would not vary much, except for the fact that concrete is a more expensive material, so it is assumed that the covered outdoor space of the concrete alternative would be slightly larger. In addition, some preliminary design loads were considered in the evaluation of each of the alternatives. Using design codes and standards, a few school loads were selected and used in evaluation. Now to go back to the design parameters that were mentioned previously, so again, there are 5 design parameters. As you can see, construction and maintenance costs are the highest of the parameters at a weight of 5, and space efficiency and environmental impact are the lowest considerations, with feasibility falling right in the middle. So under the construction cost, we considered excavation cost, material cost, labor cost, anything that would result in the construction of the building. For maintenance costs, the considerations were obviously repairs, just normal wear and tear repairs and maintenance, additional repairs if there were like a natural disaster, and then there was also consideration for an instance in which the occupancy of the building was changed with the desire of the client. Perhaps maybe the classroom setting was not what the client wanted the building for, and then they converted it into something for the athletic field or something along those lines. For feasibility, we assessed the availability of each of the products and materials that were used for the alternatives, as well as the amount of labor that would be needed, and then the time of the construction. For environmental impact, we evaluated carbon emissions, recyclability, waste management, a few other things as well, but those were the main ones that really impacted which alternative was selected. And then for space efficiency, we looked at wasted space, as well as just the efficiency of getting through the floor plan. So in an evaluation of all of the alternatives, it was concluded that the single-story steel alternative ranked higher than the rest in almost every category, tying with a few. Some key notes about this is the fact that steel is a cheaper material than concrete, which is why the steel alternatives were slightly cheaper than the concrete alternative. Additionally, it's more expensive to implement 2 floors than 1 floor, which is why this alternative had the lowest cost. Steel is a slightly more environmentally friendly material than concrete is, which is why that ranked higher in the environmental impact. However, it did not rank the highest, as a timber alternative would have been significantly better than concrete and steel. For maintenance costs, that was another notable difference, was that steel tends to do better with rusting, weathering than concrete does. So the maintenance costs typically are lower for that, as well as maintenance costs for a single-story alternative are usually less than a two-story alternative. So then, when evaluating our alternative, the construction cost of the single-story steel alternative was about $6.8 million. However, considering the 20% contingency, our alternative was slightly over $8 million. And now we will hear from Allison.
Versus engineer for across the street engineering. As a reminder, the project scope for the water resources portion is to manage water quality volume and flood control volume within the site watershed. It's also an owner preference to treat stormwater runoff for heavy metals, specifically cadmium, copper, and zinc. And of course, we're looking to comply with the City of Valparaiso Technical Standards Manual and the Stormwater Management Manual. Since the last time we spoke, my watershed has changed slightly. If you recall, I had a quite large watershed originally. It was about 41 acres. I've now reduced it to a smaller watershed that's of more concern, which is pictured here. It's about 5.6 acres, and it is most concerned with the 35,000 square foot academic building, the 70,000 square foot parking lot, and not pictured is the 62,000 square feet for the Chapel Drive extension. And so with that, I have a new water quality volume and flood control volume. For water quality volume, I'm looking at 1,433 cubic feet. And for the flood control volume, I'm looking at a little under 112,000 cubic feet. When evaluating alternatives, instead of evaluating, say, alternative 1, alternative 2, and so on, instead I opted to evaluate each method individually. And so I divided those methods into whether they manage water quality volume or manage flood control volume, and then I evaluated them based on the criteria seen here, which is essentially the same between both categories, except I have one additional criteria for managing water quality volume. So for both, I have management abilities, construction and maintenance cost, safety, runoff treatment, and aesthetics, and the additional one for managing water quality volume is green practices, because the EPA recommends a few specific practices to satisfy green infrastructure. Here's the ranking of alternatives. On the side of managing water quality volume, I chose the top 3, which is the rain gardens, the infiltration trenches, and a wet pond. For managing flood control volume, you'll see I only have one method that I evaluated, and it was because, if you remember, I was able to eliminate a few other flood control volume methods pretty early on, such as underground storage, because it just didn't fit the site. And so even though I only evaluated one method, I still think that this is the most preferred method for this site and project. It still scored above an 80, which is what I was looking for. Here are some of the deciding factors that helped me choose these methods as the preferred alternative. With the rain garden, cost was a big factor because, as you'll see in my cost estimate, rain gardens are pretty inexpensive to implement. And for both the rain gardens and infiltration trenches, safety was a big factor because they pose virtually no risk. For runoff treatment, both rain gardens and infiltration trenches are highly recommended, specifically with the removal of heavy metals. Green practices, both are approved by the EPA for green infrastructure. And then as well, as you'll see in my overall schematic in the next slide, the rain gardens and the infiltration trenches are the most visible, with the rain gardens being neighboring the building and the parking lot, and the infiltration trenches running along the Chapel Drive extension. So aesthetics was a huge factor for the university. Then with the wet pond, cost was a big factor when comparing to other similar methods. It weighed out differently from other methods, and runoff treatment was a good factor for the wet pond. For the detention basin, it had great management abilities. Cost was not so much compared to other methods, and runoff treatment. Here's an overall schematic of the preferred alternatives. Here we have the proposed preferred alignment for the Chapel Drive extension, and running along that Chapel Drive extension is infiltration trenches, with a few culverts. I have rain gardens neighboring the building and the parking lot, and a wet pond just south of the building and parking lot, and a detention basin on the east side of the project for flood control. For the construction cost estimate, I used the US EPA Stormwater Best Management Practice Standards and the Penn State Stormwater Project Cost Breakdown to estimate the construction cost. For the rain gardens, it's looking to be about $28,000. The infiltration trenches, $138,000. The wet pond is looking to be about $108,000, and the detention basin, $155,000, for a grand total of $428,000. And then with a 20% contingency, that would put us at a little over $1 million, with it being exactly $514,000. But of course, that is up to change in the future. Thank you.
So talking about costs, our design cost for this next semester will be $101,300, and construction costs, when summed from each of our individuals, will be a little over $12.6 million, with 20% contingency that comes out to $15.2 million. At this time, we're open for questions.
So on the transportation side, Joey, so you have the stop sign over on Silvady. What volume of traffic do you need, kind of like east-west, to like let you say consider a stop sign, right, versus not having any, four-way stop, right? So I don't know, I'm not being very clear in the question, but what is the difference between just having it be like straight through and a two-way stop, right, from the sides, and then a four-way stop?
Yeah, so within the IDM, I didn't see anything as far as that you needed a certain number of counts, like in order to make that difference, but since there's so many left turn movements and right turn movements coming from the eastbound approach, that was really what caused that high delay. Since then, people who are trying to turn out of Chapel Drive, they have to, cross the multiple lanes of traffic and make sure that people aren't coming, and so that's kind of why this always stop ended up being better, is because there were so many turning movements. But I didn't see anything as far as the counts in specific. Does that help answer your question?
Yes. How about over also on Silvady, your intersection there too, like with that little dead end street, right, is coming in, and then having traffic coming across.
Yeah, so the tough part is that we didn't receive any traffic counts from the city as far as Boilermaker Court goes, but we assumed that it would just be local traffic to those few businesses, so that approach doesn't have quite as many counts, but the eastbound approach does have a lot.
So,
question for Noah. So talking about stops, so you said you have a one-way stop was your preferred alternative?
yes.
And so that means that, could you go to the sketch or schematic?
Yeah, so it would be stopping on the eastbound approach, and then the northbound and southbound approaches would just move freely. They would not have to stop.
Okay. I mean, it seems like there would be so much traffic there, you'd be waiting forever if you were to stop. What?
Yeah, I ran it in G-Strom,
Yeah.
and you can see here. So it'd be these two values. So here you're waiting about 17 seconds to turn left,
Okay.
and the traffic volumes are so little for eastbound traffic, but I think it's worth it.
Okay. And that's using what, like peak volume traffic that's
So it's
projected
the PM peak, so it's the peak hour,
okay,
and it's projected 20 years into
Okay.
the future to account for growth.
okay, thanks.
That's for sure.
Let's just pound on the transportation policy. On that, I know you did, that big curve down there by the hotel, you said something about a 6% super elevation?
Yes.
Is that,
The maximum allowed is 8%. And also talked to Professor Gross and my technical advisor, and 6% is okay.
okay, seems a bit much, especially in this region, because of, you get a light on there, you slide down. I don't know if you've ever driven on highways where you come to a curve and you can't stay on the road because of super elevation. Okay, well, if it's within standard, that's good.
That's what I was-
So I had a question for Bella. So you considered what, concrete and steel buildings? So I'm just going from presentations in other years, where they're talking about like if there was a fire, like, and I just remember timber would last longer than steel, but what's the difference? It seems like there would be some safety differences there between if there was a big fire, would steel be less safe than concrete, or?
Right, so in that instance, I did consider that component of safety under my maintenance cost, because just in evaluation, to me, safety is like if I'm going to design a building that will be safe for all users and that it will meet standards. So then in doing so, I did assess that obviously there are instances in which there are disasters such as earthquakes, floods, and stuff like that. In an instance like that, the building would just most likely, no matter which material we're using, it will require significant maintenance costs. So that's why I kind of grouped those together. As far as steel compared to concrete, steel is less fire resistant than concrete. So in an instance like that, steel would not outweigh concrete. But in other instances, such as the ones I mentioned, like weathering and stuff like that, which are more likely to occur than an extreme fire, steel did outweigh concrete. Obviously, for this presentation, none of my alternatives were timber, so there was slight consideration when evaluating environmental impacts and material, but I did not take a super deep dive into those because it was not an alternative that was listed. It had been ruled out previously.
Okay, thanks. And Allison's not available for questions? Okay. Any other questions? Okay, thanks.